Okay, so where are we on today's lecture, right? So we started with just a warm up on unsupervised learning. We did a warm up of embeddings through autoencoders, and then we spent I guess half an hour on variational autoencoders. And if not the mathematical details, you should get the idea that we care about sampling and generating new images potentially from a black box which has hopefully been trained on a corpus of images. So that new images cannot be just slight noisy versions of the old images. Okay, that's not a very interesting thing. So to get there, we had this notion of reconstruction loss and a KL divergence term, which hopefully could help us get to this black box, which generates new images. Okay, and the next idea is on again sampling new images. So go from a corpus to some black box. From that black box, get new images, new faces, new pictures of the world, and so on. Okay, that's the goal, and you can actually almost do it. And we'll look at this notion of a generative adversarial network. Again, relatively new concept, 2013-14. Okay. Um, so what is the idea? Okay. So the idea is instead of so in VAEs there was some explicit notion of a conditional distribution. In particular, the z variable was we wanted to fix it to be a Gaussian distribution, and then everything else was some sort of a conditional distribution, right? The output was something x condition on z, and the input was like z condition on x. Okay. So now we're going to kind of ignore all sort of distribution assumptions, and we want to kind of create this black box without thinking of distributions. Okay. And in particular we'll take an adversarial or a game theoretic approach. They mean the same thing. Okay. Adversarial just means it's as if you have an adversary or a competitor or a opposite person who's trying to kind of win against you and you're trying to win against them. Okay, so whatever your goal is to create this black box which produces samples, but there's going to be an imagined an adversary who's going to try to prevent you from doing so. Okay, and it's basically game theoretic just means like there's a game going on. Okay, for us for our purposes. So what's the idea? Okay, so let's look at the left side of this flow chart, going from bottom to the top. Okay, so let's say we have some input which is real data. Okay, so maybe X is sampled from PD. Okay, PD is this real data distribution which may not have a handle on. Okay, if that's the case, we'll have this module which we're calling it as we'll call it as a discriminator soon, but we'll have a module or a function which is D, and it takes this input. If it's generated from the real data, takes that input and produces a number between 0 and 1, and if the input is from real data, it will produce a number which is close to 1. Okay, so that's its job. The function hopefully will set its parameters such that, and we'll learn these parameters soon. Okay, its parameters are such that if it's a real image, basically think of all my corpus. Okay, if I pass all my corpus as in all my training data, then this function should always produce a number which is close to 1. Okay, so that's the goal for this function D. But at the same time, the D has another task. Okay, now let's look at the second flowchart from bottom to top. Okay, let's say now there is an opponent. Okay, so the opponent's input is some noise. Think of it as a normal distribution, but for us, we don't care about what the distribution is for now. Some input. There's another function G. Okay, this is an opponent function. Okay, that function has to produce some X. Okay, it's just a think of a mapping from Z to X. Okay, and it's going to become important for us later on. But ultimately, some random number, it's as if this function is actually a random number generator or something, produces an X. Okay, so this essentially the G is essentially like a model. Okay, this it's like X is almost like getting from a model, but there's not really a model here because it's not a. I'm not assuming it's Gaussian. I'm not assuming some specific functional form, right? Somehow it's just taking some random number and producing an X. Okay, but implicitly it's like a model. And when I pass that X to this guy, D, that D should make that number close to 0. Okay, for this X, D of X should be close to 0. Okay, that's the goal. Okay, so for real data, D tries to this is first goal. D tries to make that make the score close to 1. For data generated by this opponent G, okay, X is generated by the opponent G, D tries to make the score close to 0, and G itself tries to, set itself up, maybe change, learn something or something. It'll also have parameters. It'll change itself so as to make D try to, so as to kind of indirectly try to make D output 1. Okay. So G's objective is to ensure that my output is as good as what D used to do with the real data. With real data, D was trying to make its output close to 1, but G is going to change its parameters such that, even with what it generated, D will output some number which is close to 1. So G of Z, just think of it as X, okay? G of Z is just X. Okay. So now this is a flowchart point of view. Now we'll get back to again a block diagram point of view. Okay. So this G is called the generator. Okay, is a generator, and D is called the discriminator. Okay, so two objects, generator and discriminator, are going to be some sort of opposing sides of a game. Okay, two players essentially, and as I said, D takes a value between 0 and 1. Okay? In fact, I should put a square bracket here. Now, here's a picture. So first three slides, first 3 points of view are going to be simple picture based. So here's the deal. So think of these dots as real data. Okay. I mean, in this case, you can clearly see it's probably a Gaussian, right? These black dots is real data. Okay. For that data, the D function has to output 1, right? So ignore the green line for now. So how would I output a 1 for this? I can think of a blue function which is like 1 here and 0 elsewhere, right? I can do that, right? Now think of G coming into the picture and saying, okay, I'm gonna start producing excess. Okay, I'm gonna start producing excess from noise essentially, such that the excess seem as if they are being drawn from this green curve. Okay. Now D is an issue, right? So because for D, it has to set it to 0 on the green area. Okay, D should output D of X. This is X. Okay, X is one dimensional. If here is the most likely values of X. For these most likely values of X, D should be set it to 0. Whereas for most likely values of real data, which is this region, D has set it to 1. So how would D look like? D would be a function which is like this, okay? Which is like, oh, I'm trying to set it to 0, at least for many of these guys. But the moment there is more, information, when there's green output, I want to set it to 0, basically. Okay. Of course, if green is exactly overlapping with the black dots, then D cannot do anything, right? D can only, it cannot set simultaneously 0 and 1. Maybe it will set it half. Okay. So that's the one-dimensional intuition. Now we'll look at intuition, which is, I guess, 2 slides. What is the generator network? I'm calling it a network, but that function is trying to fool the discriminator by generating real-looking X's or real-looking images. Okay? If generator produces almost real images, then D will have a hard time to set it to 0, because D is trained to also set for exactly real images set to 1. Okay? If generator is able to almost generate really realistic images, then D will have a hard time to set it to 0. Okay? And but what was the original goal of the discriminator? As you saw 2 slides ago, discriminator for real images has to set something to 1, and for things which are not real images has to set it to 0. Okay, not real images are essentially fake images, which is what the generator is trying to generate. Okay, so real images, discriminator wants to set it to 1, and for fake images, as in the things from the generator network, generate something, set it to 0. Okay, so here's a picture again, 4th picture, I guess. So this is what the blocks will look like. Think of Z as some noise. Okay, I'm not going to say it's Gaussian or anything. It's some noise, and there is this this guy will have some parameters. This is the one the generator function, discriminator function, and this is the real world images. Okay, and this discriminator will say real or fake. Real, let's say, is 1, and fake is 0, close to 0, and in between is like it's not sure. And whatever it says, you can have a loss saying, oh, if it was actually real and it said real, then it's good. If it's actually fake and it's fake, it's good. But if it says opposite, then it's bad. Okay, that's how a loss function. We'll see how the loss function looks like. Okay, and yeah, so what we are trying to do now is to somehow figure out the parameters of these two guys. Okay, our goal is to somehow do some learning, figure out the parameters of these two agents or these two, I guess, players or these two functions, such that generator is producing realistic images and discriminator is still able to distinguish between the realistic images and the actual real images. Okay. Ultimately, we care about this guy because from here, if it produces realistic images, I can flip some coins. I'll basically generate a random number and generate a sample because again, this guy is almost generating realistic images. Okay, so I want to set this guy's parameters as good as possible to generate realistic images. This guy's parameters as good as possible to discriminate between realistic images and real images themselves. Okay. So this is like some indirect form of learning. Contrast this with some sort of a VAE style method where you generate a sample, okay, some image, but you directly have access to the training data and you do some sort of a reconstruction error as a quality of how good the decoder is in the VAE. Okay, so that's not the case here. There's some indirect way of giving feedback. If the image is not real enough, I get a feedback like this is bad. Or if it's like really good, really good looking, a realistic image, then you get a good feedback. Okay, and your parameters are in the right region. So here's an example. Yeah, let me actually make this plus for simplicity. Doesn't matter. So just think of it as a gain, like some sort of a reward function. Okay. So what is the reward for the discriminator? The first I'm saying if your data, so think of like let's say I have two data sets, okay, real data and realistic data that was generated from the generator. So real data I'm calling it p subscript d. The data from the generator I'm calling it p subscript n. Okay. So on the real data, I want d to be close to 1. Okay, it's like the log probability. So d of x is like a probability of how real it is. So I'm just saying that log probability, log likelihood, increase it for the real data. And here I'm saying 1 minus, so this is like the likelihood of it being real. So 1 minus that is the likelihood of it being fake. That is what I want to maximize. Okay, it's like basically maximizing the likelihood of real on the real data, likelihood of fake on the fake data. Okay, that's what, and there will be parameters here. Whatever the parameter symbol is, I'm see it in the next slide, and those are the ones you need to kind of set. Okay, and what is the objective function of the generator? It's just the opposite of the discriminator. Okay, in the sense of if generator set some parameters for which so generator had some parameters and for which it ultimately it generated something and that got evaluated as fake and it was actually fake, then the generator is not really doing well. Okay, generator fake but it got classified as a real, then it will get a positive score because here it will be negative. Okay, so that's something like that. Okay, so here's the optimal strategy for the discriminator at equilibrium. Equilibrium just means the objective of the generator and the discriminator are opposite of each other. So I expanded out the objective of the generator, and the objective of the generator is just the opposite of the discriminator. Okay, I expanded out the objective of the discriminator. Sorry. Okay. So what is an equilibrium? It's like it's a two-player game. Okay. Discriminator is trying to say something, and generator is trying to say something. First, the generator produces a image. Discriminator will say real or fake. That's the game. Okay. If generator always will produce fake images, of course. If it suddenly discriminator says real because it's confused, then generator gains a point. Okay. If discriminator keeps saying fake, then generator can kind of loses point. Okay. That's what's going on. And the discriminator doesn't always say 0 or 1. Okay, it doesn't always say fake or real. It may say some number in between, 60% fake or 50% fake or 40% fake. So that number for a given input, the best thing that it can do is some sort of a ratio like this. So what is this ratio? So let's go back to that Gaussian distribution example. So let's say this was the real data. Okay, and let's say the generator produced the data which is according to the dashed sorry, the solid line. Okay, this is g of x. Okay, now if we pick up, let's say, a specific x value here. Okay, this is what g of x, so this is the likelihood of the that x under g of x, the fake thing, and this is the likelihood of that x coming from a true distribution from the real data. Okay, so for the given x, there's this much chance that it will be from fake data set, and this whole thing has a chance that it will be from the real data set. So what can I guess? Let's say this is 40% and this is like 70%. I can only say, oh, then it is real with 70 divided by 70 plus 40, right? Out of 110 observations, 70 of them would be real. Okay, that's roughly the intuition behind this equilibrium is what I'm trying to say. Okay, and what is the optimal strategy for the generator? The generator's optimal strategy is to actually get that solid thing to be exactly matching the dotted thing. If it matches, then discriminator cannot say anything. In fact, discriminator's optimal strategy is to flip a coin and say, yeah, it's 50% real, 50% fake, which is like you don't know whether it's real or fake. Okay, that's what we saw. Like shift that solid curve to the little bit left, and if they overlap, then that's the strategy. Okay, so that's what generator wants to find. Okay, but we don't know. So first of all, we don't know PD of x. We don't know the real distribution of images. Okay, we don't know. And we don't even have a direct handle on P of M. We just have a generator, and it's going to be a function. It's going to be a neural network essentially. So we'll have to change its parameters. Okay. So, and that's what we'll do. So we'll try to change the parameters of the discriminator function. We'll change the parameters of the generator function. Discriminator parameters theta d, generator parameters theta g. Okay. And how do we do it? We'll create a mini batch of real data and generated data. Those are the two data sets. Given mini batch or just a batch of real images and realistic images or fake images, we know how to evaluate the objective function because there was two terms in the objective function, one related to the real data, one related to the fake data, right? So we can score the objective value, objective function, and then take the gradient with respect to the parameters of the generator. Sorry, gradient with respect to parameters of the discriminator to update the parameters of the discriminator. Okay. Similarly, we can update the backdrop to update the parameters of the generator. Okay. So here's a ugly mathematical detail. It's basically the same term as before. This was the same as before. Okay. Except now we have put all subscripts. Okay, this one, the subscript, and this thing, the subscript, and so on. Okay. But it's the same objective as J of D that I wrote before. Discriminator is trying to maximize this objective. Generator is trying to minimize this objective. Okay. And that's why we wrote a min over the generator's parameters and max over the discriminator's parameters. Okay. And so this is what you want to optimize for. And this looks like, okay, so from intuition point of view, all we're trying to say is that we need to set parameters, but one set of parameters trying to maximize the objective, one set of parameters trying to minimize the objective. That's all. It's a little bit of slightly different from a regular optimization problem. And so for one set of parameters, it's going to be gradient ascent instead of descent. Okay, that's all that changes. Okay, this is just a heuristic, by the way. This whole computational procedure is going to be a heuristic in general for neural networks. Even if there is no neural network, sometimes it's hard to do these steps and actually get to the equilibrium. Remember, the equilibrium is what we said a slide ago. So this is the gradient ascent on the full objective. Gradient descent only on the second objective because first objective has nothing to do with the realistic or fake images, basically. Any questions about this part? Okay. So this is a training procedure. When you are not training generator, you have samples, both samples, and you're just updating the parameters of the discriminator. Okay, the two parts of the objective function. Now, when you have the generator, then you are not training the discriminator, but just changing you only care about how did it do on the samples that it created. Okay, that's the two procedures, and that's it. And what is the generative architecture? It's basically the same architecture that you saw in the VAE's decoder side. Okay, it's basically going from some random vector. I just need access to randomness because I need to create random samples. Okay, but I'm not saying that this has to be Gaussian distribution. You can assume it to be Gaussian distribution. That's fine, but there is no further variation assumption or anything like that going on, um, because it doesn't really play much role actually. Um, and what does the architecture itself look like? You want to go from a vector to an image. Okay, so this is the vector and this is the code or the vector, and the output is an image. That's the generative architecture. The only randomness is code I can just randomly kind of generate, or maybe even deterministically if you want. And I have an image, and hopefully the image is realistic enough that the discriminator is fooled. Okay, so that's it. And with that, uh, here is an example of this is from 2015, end of 2015. It's called Deep Convolutional Generative Adversarial Network. Okay, and what is this picture trying to show? Let's just focus on. Um, yeah, let's just focus on one image. I don't know any of the images that you can see. Yeah, so maybe here on any of these rows you can see you're basically showing pictures generated by the generator as you change z. Okay? So z is a vector. In this example, I don't remember what's the dimension of z. It's a vector. Start with a z. You got some image. Looks like let's say this is a bedroom image. And as you kind of slowly change z, the bedroom is transforming to a different uh, room essentially. Okay? So windows is kind of closing up and something else is coming up. So these are generated images. These are not real images, and they are not even slightly perturbed versions of the training data. Okay? So because that would be a very easy task, right? I mean, slightly perturbing a regular image to get a realistic image is not trivial. Okay, you can just add noise, but that's not a realistic image, right? So that's the big thing. And this is another example where once you've trained it, you have z vectors corresponding to these guys. Then you can, I mean, getting the z vectors is difficult, but if you had z vectors for these guys, then you can get an image which is not in your corpus with somebody with sunglasses with them. Okay. And let's not worry about this page. Yeah, there are multiple such like training of such generative adversarial networks. So at any given point of time, you would have a bunch of parameters of the generator, right? So you can always detach it and see what is the images is producing, and you can see that initially it's producing somewhat rubbish, and it's kind of producing better and better images as you kind of train more and more in this game manner. Okay. In fact, the code is also there again in I think the PyTorch tutorial webpage. So there's a code on DC GAN based GAN training, but I think it takes a long time. I think 30 minutes or something. That's why I did it last semester, but I'm not going to train it now. But you can train it on our machines if you want. Any questions so far? So next, I'm going to spend. Um, so there's two slides on the difference between GANs and VAEs, but I'll try to explain it by just a picture. Okay, this is the last part actually. Um, So if you look at VAE, is going from an image to a latent space. Here we are assuming a strong assumption about, like to get these two parameters, we are assuming something about distribution assumption about the latent variable being Gaussian, and then we are trying to reconstruct, of course, but we are also, once we train it, then we can sample a Gaussian from here, pass it forward, and we get a new image. Okay, that's the idea. And the interesting thing is for VAEs, you can, given an X, you can find, given an image, you can find what is the latent embedding. Okay, because there is the encoder part. Right? Given an image, it will tell you what the mean and the variance of the Z random variable should be. Okay, and you can interpret, so VAEs also are in the land of probabilistic distributions, right? So because there's a distribution of Z, there's a conditional distribution of X given Z, there's a conditional distribution of Z given X on this side. So there are there's a distribution, joint distribution with Z and X which is being considered in this VAEs, okay? But the problem is empirically people observe that it's blurry images mostly because the output of a VAE you're assuming it to be a Gaussian. Okay, so if you draw from a Gaussian, you generally don't get a sharp image. Okay, um, GANs on the other hand, if once you train it, they give you very sharp images. Okay, what's the idea of a GAN? Some distribution could be also again standard normal if you want, but this is not very critical. You generate a bunch of images, and there is a corpus of real images, and discriminator tries to say that it's zero for this, score is zero, close to zero for this, and score is one for this, and you want to train this parameter such that indirectly, such that train these two parameters such that this guy is producing images which make the discriminator not score it flow. Okay, so that's the game being played. But the good thing is you get sharp images in this type of a training. There's no Gaussianity stuff going on at the output, for example. But the problem is, given an image, you don't know what the latent vector is. Okay, you can't figure out like what's the. I mean, you can actually figure out if, but you have to do backprop. Okay, because it's a network, right? You have a network. You know what the output is. You're asking what is the input which led to that network. You can do that. Okay? We did that for debugging of CNNs, right? But it's not trivial. Whereas here you just have to pass it forward and you get the Z embedded vector. Okay, so that's the difference between VAEs and GANs. And as I said, both models are recent. VAEs from 2013 and GANs from 2014. Uh, Relatively recent in terms of how things go. They have a lot of impact in applications, especially in computer vision. Actually, the versions that we saw are the vanilla versions. There are actually many variations of VAEs and GANs, sorry, uh, which can be used for super resolution. Okay, those are not tasks where it's a random sample of an image. Those are tasks where there's some already input image. You want to kind of sharpen it or make it less blurry. That's super resolution, right? So that's not a vanilla application, but you can do that. It's also used in RL to figure out like sample what's the future look like, for example, because you can get samples of situations, right? I mean, whatever corpus you're training from, you can get samples from there. You can actually plan. Okay, the next three lectures are about reinforcement learning after the exam and so on. So we'll look at what that is if you don't know. You can create embeddings, the Z vectors, and generally artistic help and stuff like that. Okay, and at least the researchers who work on this, their goal is to really create this black box which will actually create very realistic real world images. Okay, physical images, which is kind of a very hard task, but they're able to get there for at least narrow domains. Okay, faces and stuff like that. So that's it for today. Any questions about the content so far? Too much stuff?
Can you use VAs or GANs for other things besides images, or is that pretty much all they do?
No, you can use it for other things. Like you don't have to work with images, but then you don't have to think of them these as correlation networks or things like that. But for like other data, for example, the regular structured data, you don't need. I mean, you don't need. Uh, Definitely, probably don't need GAN style of box because you can assume parametric distribution on structured data, for example, because you know what the variables mean. Here it's pixels, so you don't know what's the distribution on pixels to what's the distribution on real images. That's kind of a hard object to think about. But if you have features like income, age, things like that, then it's kind of not difficult to think about.
Overkill.
Yeah. But people can train it to non-image data as well. It's just that you have to choose different things on generator and discriminator side. Yeah. Okay. Thank you. So next week the exam is in the same room.